Alright, in this one, I want to discuss how you can derive the formula for kinetic energy. So we say that Ke is equivalent to 1/2 mv squared, right? And this is a very, important equation, right? I mean, this is found in classical mechanics, well, classical physics in general. So you find in thermodynamics, for example. And even it even is in quantum mechanics. You'll find in the form of p squared over 2m, but they essentially have the same meaning. But yeah, so I mean, you kind of want to know where this comes from, right? Like, why do we have to have the mass, and why have to square the velocity, and such and such. So, well, I'm going to do it through two ways. One way would just be through simple algebra. The other way would be through a little bit of calculus, so derivatives and integration. So yeah, so the first method I'm going to look at. First method. So we know that work is equivalent to force times distance, right? If you have a force and it's moving some distance, then it has work. It has energy as well. So another equation that's we're going to look at is the sum of the forces is equivalent to mass times acceleration. And we're just going to consider one force, so we'll just say F is equivalent to ma. So F equals ma. So now we can actually just kind of take this and we can replace it in for the F. So now we just get work is equivalent to ma d. So now if you look at this AD term, it kind of has a linkage back to kinematics, right? The equations that describe motion of an macroscopic object. So AD or 2AD is equivalent to your final velocity squared minus the initial velocity squared. So it's the difference of your the difference squared of your velocity. So and also recall that v final minus v initial squared is not equivalent to that. These are two separate ideas, right? So well, now we know that, we can kind of just isolate for AD. So you simply just divide both sides by 2, and you get AD is equivalent. Well, you could just write it like this. I'll just write it as 1/2 v final squared minus v initial squared. So, now we have final and initial. So kind of the assumption we're going to make is that we have an object. It starts with 0 meters per second, and it accelerates to some velocity v, right? Some velocity vector v. So what that means is we can kind of just get rid of this, and then our v final would just be v. So we would have AD is equivalent to 1/2 v squared, right? Make that 0, and then make this just the final velocity, v. So now when we have this, we can kind of just put this back into the equation. So work is equivalent to mass times AD, which is 1/2 v squared, and it's looking a lot like kinetic energy formula. Now we can kind of just rearrange it. So 1/2 mv squared. And since we're assuming that we have some velocity, we can also assume that it has kinetic energy, right? So we can kind of just replace this with Ke equals 1/2 mv squared, right? Because if it has some motion, then it is kinetic. It has kinetic energy. That is the definition of kinetic energy. The energy possessed of an object if it has motion. Yeah, that's the first way of looking at it. The second way, number 2, the second method is through a bit of calculus. So I'm going to say that work is equivalent to force times distance. I'm going to use S instead of D because Well, if I'm going to use derivative notation, so if I had d, then that would be confusing. It's better if it's ds. So now what we can say is that if work is equivalent to force times distance, then an infinitesimal change in the work is also equivalent to a force times an infinitesimal change in the distance, right? So now we can say, well, again, we can say that the sum of the forces is equivalent to mass times acceleration. We'll make the assumption that we only have one force, because, here in the work formula, we only have one force, so F is equivalent to ma. And again, so now we have force here, we have force here, we can plug it in. So we'd have dW is equivalent to ma ds. Okay, and now we can look at this acceleration. This is when more of the calculus comes in. So if you have an acceleration vector, you can think of that as the instant, the very small change in your velocity and the very small change in your distance, right? That's your instantaneous acceleration. So now we know this. Again, we can just bring this back into the formula. So now we would have your very small change in work is equivalent to mass times your acceleration dv dt times your ds. So now you have dw is equivalent to, and I can just bring this ds like on the numerator. I don't have to do it with the mass because it's a different thing. So dv ds all over dt. So we said that dv dt is acceleration. The whole reason why we did this was so that we could keep that. So we're not going to change that. But now ds dt. So we said, so if distance over time is equal to velocity, right? So then that means that your infinitesimally small change in distance and your infinitesimally small change in your time is equivalent to velocity as well, your instantaneous velocity. So now that we know that, we can replace it out. So we'd have dw is equivalent to you'd have your mass times your velocity v times dv, right? So now this is when the integration comes down, because we have v dv and we have dw. So if you remember, the integral of, I'll just use the v dv. The integral of v dv, so that is equivalent to, essentially it's, what would you call it? I guess you could call it the anti-power rule. It's, you add 1 to the exponent, so it becomes 1 plus 1 here, and then you divide by that same exponent that you incremented it. So if you have v squared, because you add the exponents, and you divide by that same quantity, you get over 2. So that is equivalent to 1/2 v squared. And again, it's looking very similar. So here we take the integral of both sides. Since we're not taking the integral with respect to dv, or with the mass, sorry, we're not taking the integral with respect to mass, we can say that we can pull it out. So the indefinite integral of infinitesimal work is equivalent to mass times the indefinite integral of v dv. So now once we have that, we can replace this with what we just found, which is 1/2 v squared. This would be just work. So work is equivalent to mass times 1/2 v squared. And just do a little bit of rearranging. We can also make this ke. We can just, because we said that if something has velocity, it has kinetic energy. So we can rearrange this, and there you go. You get the same formula through, somewhat different ways. But yeah, that kind of shows you how you arrive to this final beautiful equation. So yeah, I hope that helped, and bye.